Today I want to give a tip about using Openhole well log data to estimate reservoir properties. My name's Kurt Meir, and sometimes when you're studying a reservoir you don't have direct measurements of all the fluid properties and reservoir properties, so the Openhole log can give you some basic information. So let's take a look. Here's an example of the log header from an Openhole log. You can learn a lot about the well and some information about the reservoir. The name of the well, who drilled it, where it's located, the surface location, and very important is the date that the log was run and the depth of the logging run. In this case, it's 10,730 feet. And there's other information, but some important information is the type fluid in the hole, and the density is 10.2 pound per gallon. So that's the weight of the drilling mud when they drilled and logged the well through this depth. And then some other information you can get is the maximum recorded temperature at the bottom of the hole from the logging tool. All right, when you're estimating reserves, you need to know the reservoir pressure. So how can we estimate this using well log data? Well, we know the well was drilled and logged with 10.2 pound per gallon mud, and usually you drill the wells overbalanced, about a 1 pound per gallon overbalance. Otherwise, you're taking a chance of the well blowing out. So in most normally pressured reservoirs, we know the gradients are about 8.9 pound per gallon. In abnormally pressured reservoirs, this mud weight would be more important to know. But anyway, in normal pressures, environments, about 8.9 pound per gallon, and you multiply that by the conversion factor and you get 0.463 psi per foot. And if you know your reservoir depth that you're studying is 9,500 feet, you can estimate the reservoir pressure using this formula. So at the time of drilling, the reservoir pressure was about 4,400 pounds per square inch. You can infer that from this logging information. All right, what about the reservoir temperature? That's important to estimate. All right, so the logging tool has a maximum temperature of 225 degrees, but we know that the drilling mud at the surface is in a pit and it's cool, and so as you're drilling and circulating, it will cool off the bottom of the hole. So the maximum temperature may not be the true temperature of the bottom of the well, because if you were to let the well be shut in longer, that rock temperature would have heated up the mud at the bottom of the hole. So we can estimate that maybe the maximum temperature at the bottom of the hole is 228 degrees. And there's some calculation methods based on circulating time that you can use for this. But anyway, this is close enough for what we're doing. 228 degrees. And we know the bottom of the hole where they logged it was 10,730 feet. So we can calculate a gradient of the 228 maximum temperature minus the surface temperature, ambient conditions of 72, and we get a temperature gradient of 0.0145 degrees per foot. But we like to quote temperature gradients in an area in degrees per 100 feet. So it's 1.45 degrees per 100 feet. All right, so if we know the ambient temperature is 72 plus the gradient times the depth of 9,500 feet, we can estimate that our reservoir temperature is 210 degrees. So the original reservoir pressure should have been around 4,400 pounds per square inch, and the temperature is 210 degrees. So even though we don't have direct measurements, we can get an estimate of these two reservoir properties when we're doing our reserve calculations. It's very important. You have to use all the data when you're evaluating your reserves. Okay, so I hope that was informative and helpful. And just please call me if you have any questions. Thank you.